So, good afternoon, everyone, and I welcome to my YouTube channel, Engineering Technology and Meditation Rituals. So, today I am going to explain the topic three moment theorem or Clapeyron's theorem, right? So this three moment theorem, I have taken one example earlier also, and you can go through that video. Today, look at this numerical. In this is a continuous beam, but there is one fixed support, and these are the two simple supports. So these two supports, these simple supports, which will offer one vertical reactive force, and this fixed support will offer two reactive forces. One will be vertical one and in this direction, right? And other will be as a moment. So in all, if you will look at this continuous beam, you will get here two spans with two simple supports and one fixed beam. So if you will refer to a Clapeyron theorem, you have only one option, that is span ABC, when you can apply the equation of three moment. But now let us try to calculate the unknowns here. This fixed support will provide two unknowns. One is the reactive force and one is moment. This is one more 3 and this is one more 4. So there are 4 unknowns, and if we try to analyze only and to calculate only the vertical forces, then there are 3 unknowns. Now this one equation is not enough, which we will apply here to calculate the unknown forces. So to develop one more equation, we imagine one virtual span, and this virtual span, if we can see here, this we call it as either virtual span or zero span. So when you you will progress with the numerical, you will come to know what is the exact significance of taking this zero span or virtual span. So now you have taken this virtual span, and this is your support. You can call it as imaginary support, say A dash. So now you have two spans available, right? A dash AB and ABC. So definitely you will get two equations of Clapeyron's, and you can determine the unknowns. So see here, the first step in Clapeyron's theorem or three moment theorem is to calculate the bending moment diagram. So this 6 kilonewton per meter is uniformly distributed load, and 4 meter is a span. So for span AB, the bending moment calculated will be equal to W6 multiplied by L square, that is 4 square by 8. So it is coming, see here, it is coming 12 kilonewton meter. If you will look at this span BC, the same UDL is there with span 4 meters, and the shape is parabola because it is the equation developed will be of second degree. So this is again 12 kilonewton meter, right? So these are the bending moment diagrams which are plotted by using very simple equation WL square by 8. That's it. After that, the first equation will be applied on this span The first span is A dash A B. So our equation of three moment will be MA dash multiplied by span, that is zero span, virtual span. It doesn't exist, we have created that span, imagine, plus 2 times MA. See here, I will try to show you, because we are considering A dash A B, so it will be MA dash multiplied by 0 plus 2 times MA multiplied by 0 plus this, that is 4 meters, plus MB into 4 meters, that is equal to 6 times A0 x0 upon L0. This is the area. A0 stands for area under the bending moment diagram. You please refer my previous numerical first and then listen to this video. You will understand in a better manner. Then x0 bar, that is the distance of centroid. This is for this span, and this 6a1 x1 bar by L1 is for this span A, B, C. So look here, these values are from here. This is 0 into M0 is 0. Span L1 is 4 meters, so 4 into 2 8, right? This is 8 MA plus MB into L1, that is 4 into MB, equal to 6a0 x0 upon L0, that is 0, plus 6a1 x1 upon L1. So 6a1, area under the bending moment diagram. So under this bending moment diagram, so A1 means area under this bending moment diagram, and this is your parabola. So area will be 2/3, base is 4 meters into height 12. So this will be the value of A1. So A1 x1 will be equal to, x1 is the distance of centroid from B, because we are considering span A dash AB. So this distance will be equal to 4 divided by 2, that is equal to 2, because we are considering only this span. So you will get this equation finally. 2MA plus MB is equal to 24. So this is the equation which you have obtained from the span A dash AB. Now let us proceed with the other span. Now the next span is span ABC. So for ABC, you have to apply the equation MA into L1 plus 2 times MB L1 plus L2 plus MC into L2 equal to 6 A1 x1 upon L1. Now note here, A1 x1 upon L1. So A1 is the area under this bending moment diagram, right? And x1 is this distance, that is 4 by 2, that is 2 meter, plus C2 6 into A2 is the area under this bending moment diagram, into x2 is this distance, that is also 2 meters, but it is the distance of centroid of parabola from C. So in this way you try to put your values. MA into L1 is 4. Now ABC span if you are considering, so the L1 will be equal to 4 and L2 will be equal to 4. So 2 times MB L1 plus L2 is this, plus MC, as I have explained in my earlier lectures also, that a simple support which is at end, right, the moment there will be equal to 0. So this value MC into L2 is equal to 0. 6a1 x1 upon L1 plus 6a2 x2 upon L2. You put the values of L1 and L2, that is 4 and 4, right? Because now you are considering the span ABC. So in this way, note this, A1 will be equal to 2/3 base 4 into height 12. So A1, when you are considering span ABC, this value, area under this will be A1, area under this will be equal to 8, right? So in this way you will put the values, and from these two equations you will get the values of MA and MB. Now listen carefully. At the end, at the last, you have calculated the values of moment at A and moment at B, because moment at C it is 0, being a simple support. So to calculate these two unknowns, you need two equations. If you look at this continuous beam ABC, it is not possible to develop two equations, you know. So what you have to do, you have to assume one imaginary, one virtual span. So with this one virtual span A dash, now two spans are developed, A dash AB and ABC. So with these two spans you can apply the equation of three moment. For three moment there should be two minimum spans, then only you can apply Clapeyron's theorem. That's why we have taken this virtual span, so that two equations can be developed and two unknowns MA and MB can be calculated. So as you know, the MA and MB calculated are here the hogging moments, because these are the function of supports, and these parabolas because of UDL, these are the sagging moments, because these are the function of loads. If you will overlap these hogging and sagging moments, then remember this portion which I am coloring here, this portion is the neutral portion, because negative positive, sagging moments I am considering positive, hogging as negative, so this is the neutral area, right? This area is also the neutral area, this area is also the neutral area. But if you look at this area, this is the positive area. If you look at this area, this is negative, this is negative. So this portion indicates that here the hogging moments develop, this indicates that the sagging moments develop, and depending upon the hogging and sagging moment, we decide where, in which zone we should place the reinforcement. That is the practical application of the structural analysis. So I think enough for this lecture, and the concept of Clapeyron's theorem might be clear to all of you. If time permits me, I shall again explain few examples. Thanks for watching my video. Thank you very much.